Okay. Now Dan is going to tell us more about the SpinQ. Now it is
Perfect.
just starting.
Not sure if my microphone is on.
Marianne, can you hear Dan?
Yes, we can. I can.
Okay,
So he
okay.
can start. Thank you.
Okay. The little quantum computer is still performing calibration, so we cannot run any real tasks. But maybe in the meantime, I can show you a picture of the details about the calibration of something is not working the way it should.
Kar razloži težave.
As I mentioned yesterday, it's very sensitive to temperature variations. It's also, I wanted to illustrate, okay, it's too technical. Here you can see the temperature graph, and apparently, even though we tried to keep the temperature in the room constant, it's still slowly creeping up by tens of degrees, as you can see, but that's enough to cause a problem in the calibration. Incidentally, it's also very sensitive to magnetic fields, but that's usually not a problem because it's positioned stationarily, and once the calibration takes care of the disturbances in the magnetic fields, it works
Kar
normally.
nadaljuje s tem, koliko je stabilen in take reči.
Speaking, I don't know, maybe I'll bore you with the technical details. The field inside the sample with the active molecules is a little less than 1 Tesla, which is vastly greater than the Earth's magnetic field, of course. But on the other hand, for the spins to act in unison as one quantum state, it has to be uniform throughout the sample to approximately a part in million. So this is where the problems come from. But instead of the details about the quantum core, maybe I should show you now that we have some more time how we compose the circuits and random. We have a set of gates in this line.
Bolj glas pravijo.
Is my volume too low? And what?
Can you increase the volume?
I try.
Daj ga na glas. Sprašuj, če je better, veš?
Apparently, my microphone was actually muted, and whatever you heard through the microphone on the other computer. Sorry about that. You should see me more, hear me more clearly now.
Yes, yes.
So we have a set of gates H, the Hadamard that we used, identity, I, X, which is the knot, Y and Z are the, well, we didn't talk much about them, but as X is actually a rotation about one of the axes of the Bloch sphere, so our Y and Z, they have to do with the phase of the state of the wave function. And since QBrowns doesn't go that far into the nature of the complex numbers representing the state, we don't get that deep into these gates. But by the way, for those that might find the collection of gates intimidating, we have a cheat sheet built into the computer, so we can easily look at what each of the gates does. For example, the controlled X that we talked about yesterday is represented by the matrix of that you can see here. And unfortunately, we cannot demonstrate the controlled, not the Toffoli gates that we also talked about yesterday, because it would take 3 qubits and we only have 2. In fact, the software controlling the computer also allows simulation. So in simulation, we could do that, but then there's not much point in experimenting with it because it's the same as running it in Qiskit. So, okay, just if we briefly go to the rest of the gates, the interestingly labeled square root of x, y, and z actually mean it's kind of a mathematical metaphor. They mean the operation that, when performed twice in succession, will produce an x or a y or a z. It's a half done. Like the square root of x then means the square root of naught, an operation that, when done twice, will negate the state. This is something that in classical computing or classical physics would be difficult to imagine. Then we have the arbitrary rotations about the 3 axes, Rx, Ry, Rz. That's okay. I guess if we start a new circuit, I could illustrate this was just a shortcut for clearing our line. If you were to use one of these rotations, which we do by simply dragging the icon of the gate onto the qubit line, we get an option to specify the angle of rotations, which could be arbitrary, like 77 degrees. Oops, my mistake, using the wrong. So this is now a rotation by uh-oh. Well, the computer can be somewhat temperamental, and at this point it just rebooted itself. Doesn't happen often, but sometimes it does. And now we're back in the calibration phase. I can exit this and go back to what we were doing. So we select 2 qubits, and okay, I think I have demonstrated that we can use arbitrary angles. Then we have the T and the T dagger gates, which I believe are beyond the scope of our discussion now. The controlled knot that we know well, the controlled Z, which is a Z gate, a phase shift controlled by the other qubit, and this little nice symbol actually means a swap. The state of the qubit 0 and 1 gets swapped. Maybe we can illustrate this by negating one of the qubits with the NOT gate, the X. And oh yeah, of course we cannot run the program because the calibration is in progress. So maybe I will show you some of the examples of the circuits that are in the library that comes with the computer. Okay, the 1 qubit cases are not particularly interested, but maybe as a review of what we talked before, let's, okay. The 0 state means just do nothing, because by convention we always start with the 0 state. The 1 state means starting with the 0, negate it, and we end with the 1. The more interesting, of course, are the superpositions. Okay, this is forgot it's implemented with the square root gate, but basically what we would do in the style of what was discussed in the previous sessions, we would apply a Hadamard gate. Okay, delete this one, and Hadamard gate starting with state 0 would give the superposition of 0 plus 1, and if we wanted the minus, we would start with the state 1. So we would negate the state 0 and then apply the Hadamard gate. Too bad I cannot, maybe, no. I tried to run the circuit, but as you see, I got the warning that the calibration is still underway. So maybe just so to not to bore you, I go back to the collection of examples from the library. Oh, and we go to, of course, to 2 qubits, which are more interesting. We have, again, as a quick review, the 0, 0 states where both qubits start in 0 and we do nothing, the 0, 1 when we negate the second qubit, and by extension up to 1, 1 where we negate both. Now the interesting start is, this is something we did at the beginning of yesterday's lecture, applying Hadamard gates to both, and either imagining it, the resulting state as a tensor product, or as they're still independent states. They're not entangled. However, if we apply the Hadamard gate on 1 qubit and then use a controlled knot, we get an entangled state, which is 50% of both qubits being 0 and 50% of probability. So the amplitudes, of course, are 1 over square root of 2. But in short, it's a mixture of equal parts of 0, 0 and 1, 1. And of course, it would be interesting to run this and show the results. But in fact, maybe I still have it in yesterday's results, because during the lecture, I did execute this one. So I think it, let me find it. No, we don't have any of them because of the reboot in between. Sorry. So basically, all I can show at this time are the sample cases, and so this was the superposition of entangled state, which is also
known as the Bell state. And then the next one in our list is the Grover algorithm, the search algorithm that we're about to talk about, learn today. And I can show you the circuit. And incidentally, it doesn't look exactly like the circuit we are about to compose during today's lecture. And there's maybe a funny anecdote to go with this. During one of the previous Q bronzes that we organized in Slovenia, actually our first one, we had a lecturer from Slovakia. And the workshop was organized in person. It wasn't an internet event. So we actually got to meet the lecturer in person. And the night before, he presented the Grover algorithm. We met and I showed him this circuit and said that this is how the library on this computer implements the Grover algorithm, but it didn't look like the one he was about to show. And so he sketched this circuit into his notebook and over the night analyzed it. And then next morning he told me, yes, in fact, it is equivalent. But sometimes it's not obvious to even to somebody experienced in quantum circuits that two implementations of the same idea are equivalent. Then again, I try to run maybe the calibration. Yeah, in fact, I think it will run because yes, as you can see, there's something happening here, something is turning, and we have a progress bar at the bottom that shows the progress of the computation. It takes about 30 seconds. The reason why it takes so long, those of you who, I guess everybody among you, you know that typically the operations take a very short time because even the coherence, the stability of the quantum state will not allow in this system to keep it for 30 seconds. But what really happens is that the same experiment is repeated a large number of times, which allows us to get the probabilities okay, something happened on my, sorry. By the way, how much time do we expect to, I will have to reconnect to the.
For now, we have time because Dr. Chetri is not still here. He said 30 minutes, so we have half of them at least. So yes, try and continue.
Okay, I will reconnect.
Thank you.
I may have to stop sharing the screen because no, it makes no sense. I have something weird happening on my screen. So Nico, how ти видиш мене? Shit, but то чисто. Okay.
Mariana, a little break.
Yeah.
Yes, relax, relax. Everything is fine.
Okay. Uh, yeah. It appears that the connection, the screencasting connection to our computer is down for reason that maybe the previous reboot caused some. Uh, uh, what the. Blah, blah. No, it's just not working. Yeah.
Don't be worried. Try to reconnect.
Yes. So I just tried reconnecting and the machine refused connection.
Yeah,
Uh,
yeah. Here
uh,
in the chat is written, of course, if you can make it later, and to make screenshots, and also to make a recording of how you complete the steps, and to say it to Discord group if it
yes.
is not working now. So we, of
Yes.
course, can see how the things happen in addition, because we have this server, these chats, everything will be there and will be valuable too, no matter it is not in the same time. Yeah, try again, because the instructor is not still here, so
Okay. It
we
appears
haven't
that
another. Yeah.
we got a connection,
Mhm.
although it looks kind of weird. Smallish. Uh, is my screen shared? Uh, at the
Yes, it is. We can see it.
So you can see. Okay, we're reconnected, and now we are in the collection of completed tasks, completed computations, and the one that I started just before the Grover search is here now, and you can see that the result is almost pure state 1-1. Now, it would only make sense that I explain how the circuit works and why the result. Basically, it's the Grover search is a search algorithm. It finds it's like looking for an object in a set of drawers, and the outcome probability of the various states reflects the probability that the item we're looking for is in that compartment. Now here with 2 qubits, we can simulate a desk of drawers with 4 drawers, and also something that we will talk about, that the instructor will tell us, is the Grover search is an iteration. It's an iterative algorithm. In general, the operation at the core, which is the amplification of the wave function in the desired state, needs to be executed several times. The number of times it has to be executed depends on the number of items, let's say drawers, and also the items that we search for, because we can search for more than one item in the collection. But okay, I'm talking making it sound more complex than necessary. But what I wanted to say is that it turns out that with 2 qubits and 4 states, it actually takes just 1 iteration. So we don't have to repeat that. Maybe if we go back to for example, we could run the same thing again and compare the results. And of course, because this is not a simulation, but it's an actual physical process with noise, the results would be slightly different. Speaking about, well, yes, something I wanted to mention yesterday, but I'm going back to the results that I was showing a minute before. The fact that we don't get a pure state is the consequence of the noise, the problem that was also talked about in yesterday's lecture about machine learning. And we see that with just a few gates and 1 repetition, iteration of the step, we already have some error in the results. This error would accumulate, and according to the specification of the manufacturer, we can have approximately 30 consecutive operations on a qubit and still retain validity of the results. But of course, for many applications, we would want to have way more operations, and this illustrates the need for error correction algorithms, which will be critical in moving from today's state of quantum computing to the next level. Here we cannot demonstrate error correction because that typically really takes a lot of physical qubits to implement one logical qubit, which then behaves cleanly without errors. Okay, if maybe we return to other examples from the library. Oh, yes, the one before I said we could, for example, the Bell state, the superposition, the entangled state, we could not run before because the calibration was not complete, but now we can run it, and this will be a simple example that even though we don't understand the Grover search yet, we do understand the entanglement and know what to expect from a controlled knot controlled by a start by a state resulting from the Hadamard gate. So we will verify. Okay, now we can switch to the results, and as you can see, we have a 45 probability of ending up in state 00 and 54 pending in state 11, and the other two, the forbidden combinations, are actually negligible. Now, okay, let's say as a homework for an exercise left to the reader, what would happen if we, instead of just applying the Hadamard state to the CNOT, if we negated the qubit first and then applied Hadamard? We can easily try by just moving these gates. There's still the same gates, but I just made room for another operation, the knot. And then let's run this circuit. Does anybody have a theory of what states, what combination of states we should expect? Well, in a few seconds, we'll see. Okay, the computation is finished, and here are the results. Same as before. Can you imagine why they are the same? What have we really changed by negating the controlling state? Well, one could say that we selected the row in the matrix of the Hadamard operation, but what? So instead of state 0 plus state 1, we collected state 0 minus state 1. But the amplitude was inverted for one of the states, but the probability, which is the square of the amplitude, is the same. So we have, the numbers are slightly different, 52% versus 47, but essentially we just have the 00 and the 11 state. Now, another exercise, what might we want to do to get a different combination of the states? And one thing that comes to mind is, well, let's negate the state, not the controlling state of the C0 operator, but the controlled state, like this. And we'll run this one too. We didn't. Oh yeah, it is being executed. and we have the results. And this time, the results, in fact, are different states. They are the two combined states where the qubits are different from each other, the 0, 1 and the 1, 0. And again, the other two are negligible, while these two are approximately equal. Now let's see what else. Does anybody have a request for a circuit that we would like to run, or otherwise, well, else maybe we can show, since yesterday was very quick, this interesting looking circuit. I just showed it yesterday, quickly at the end. This is again from the library supplied by the manufacturer, an example of a neural network. So it goes with the concept of machine learning. Clearly, the range of what can be accomplished is limited by the number of qubits, but it shows, it's a demo basically. And then, okay, this one I don't think I showed yesterday, or no, I think I did. It's no, let's leave that. It's I believe, but I could be wrong. I'm honestly getting a little bit confused right now. I believe it's a Fourier transform example. Okay, let's run this example, but I don't think I'll be able to explain. It's not one of those that I have used or really understood. But it's shown on the, or well, shortly we'll visualize the results. But as I said, I won't be able to comment very meaningfully on. So this is the result of the execution. It kind of looks like a sine wave, which kind of resonates with our understanding of the Fourier transform. But as I said, I am not able to explain the workings of the circuit. Then maybe, okay, another thing that may be along the lines of, no, this is too, okay, this is a kind of simple and I would say cute example. It's an implementation of the swap gate, the gate that exchanges the state of the two qubits with a combination of three CNOT gates. So as an example, I will put an OT gate on the qubit 0 so that we start with the state where Q0 is 1 and Q1 is 0. And if we are running the circuit now. If the combination really does what it's supposed to do, then we'll end up with qubit 1 in the one state, in pure one state, and vice versa. So yeah, I think I did. Let's see the results, and the result indeed shows that the 0-1 combination is prevailing. It's not completely pure. We talked about noise before, so we have 6% probability of the state not being transferred but being kind of lost, and both qubits ending in state 0. Of course, we can repeat this with the other. This basically, this combination of 3 gates does the very same as this swap, which is for which we have an icon as an elementary gate, a Lego block. But most likely, this is just a shortcut, which in reality translates into this combination when the actual computation is performed. This is fairly okay. Do we have a result? No. Oh, I clicked. Wait. Apparently, there's a question, but I can not see it. I'll move to the
I'm
other.
going to read it for you. How many repetitions are executed to get this statistical result?
The number of repetitions, I don't have the exact number, and the manufacturer doesn't specify it, but judging from the coherence time of the system, which is the order of 30 milliseconds, it has to be at least 1,000. It's probably several thousands. And okay, you reminded me to show you another thing, but let's show the results first. As you can see, again, it was inverted into 1, 0. I mean, swapped. Now what I remembered when you asked about the number of repetitions is this: if we go back to 1 qubit and well, let's run anything like the Hadamard operator on the state 1, you will see that the results are not just the bars representing the probability for state 0 and 1, but also a point on the block sphere, which represents the actual state, the state before the measurement. And here you see this is the block sphere, and it shows the green dot is the state of the system. And here you may start wondering, and by the way, the projection probabilities as expected, well, they're actually exactly 0.5. You may think, but we learned that once we perform the measurement, the state collapses and we just get one possible outcome once of the basis states. So how can you visualize the uncollapsed state on the block sphere? And the answer is, again, by doing many repetitions. Same as basically for projection probability, by running the experiment just once, we would only get a 0 and a 1, a full end bar in one on or the other position. But if we do it 10,000 times, we get a probability. Now, for the state, similarly, and we talked about this, I believe, last week, which under the name of quantum tomography. If we have many copies of a particular state, then we can measure it along different base axes and reconstruct the state before the measurements with arbitrarily high precision if we have an arbitrarily a sufficient number of identical qubits. Now, in this case, maybe so we see that the resulting state is in the direction opposite of the x-axis. We can illustrate the thing I mentioned before, that the when we had the controlled knot attached to the Hadamard state, negating the qubit before applying Hadamard gates and then feeding it into the controlled knot did not change the probabilities. But by running this this part of a Hadamard gate with or without a knot gate in front of it, and looking at the resulting state on the block sphere, we should be able to see the difference. And in a few seconds, we should have the results. Unfortunately, the block sphere is convenient only in the case of 2 qubits, of one qubit. Okay, we have the results, and as you can see, the green dot, the representation of the quantum state, is now nearly aligned with the x-axis. It's not in the opposite direction of the x-axis, but in the forward direction. So we have an inversion of phase. Even though the probabilities are the same, the phase was inverted. And oh yeah, before I was saying that if for more than one qubit, there is no convenient way like the block sphere to represent the combined state of the system. It's just too complex, too many. We would need a space of higher dimensions, and we humans don't work well with visualizing things in more than 3 dimensions. Now, okay. The lecturer is still not with us. Hello. Right. Yeah. Okay. In any case, even though you could do all those experiments in Qiskit, it's more fun to know that they're actually being performed by a physical system, and it's not just a simulation. It's somehow it gives the thing a different feel. Okay. Apparently the regular lecture will start soon. Wondering if there's anything else I can show. Okay, the gates. Yeah. Maybe okay. Since we're talking about Yeah. Again, does anybody have any questions that I can answer in the meantime?
Thank you very much. It was really interesting and also a very good presentation of something that we have seen